Very well. So our goal is to solve this differential equation. The differential equation given to us is as follows. It says, well, here we have y prime times x plus y equals to x squared times y squared. Now, how do we solve this differential equation? Is it a separable differential equation? Can I separate these variables? Take a look at this. Let me try to see if it's separable or not. Here I have x dy dx plus y equals to x squared y squared. If I divide everything by x, what I get dy over dx plus y over x equals to x y squared. Well, if I take this and then bring it to the other side, I get dy over dx equals to x y squared minus y over x. Well, the question is, how do you separate these? Is it possible to just separate x and y's? Can we do that? How do you do that? If you factor out y, you're left with one y here. If you factor out x, then it means that you end up with another x here. So it's not separable. The method of separation doesn't work here. Okay. Let's see if this guy is a linear first order differential equation or not. Remember that for a first order differential equation to be linear, you need to have a sub 1 x y prime plus a sub 0 x y equals to, well, another function in x. We bring this to the other side so you can see the whole thing. a1x y prime plus a sub 0 x plus y equals to g of x. So here I'm okay with x. I have x y prime plus y equals to x squared y squared. So far so good. X and a1 of x, a sub 0 x is just 1. So it's good so far. But when you look at the right-hand side, on the right-hand side, you have an extra y squared. What are you going to do with this guy? So it is not linear. Is it exact? Well, if it's exact, the differential form m x and y dx plus n x and y dy is equal to 0. So this is a differential form that you have. So first we need to write this in differential form. You get x dy dx plus y equals to x squared y squared. Well, if you multiply everything by dx, you get x dy plus y dx equals to x squared y squared dx. You can bring all dx's to one side and then write this in the differential form. This is the differential form that we have. Let's see. We get y minus x squared y squared dx plus x dy equal to 0. To be exact, the partial derivative of m with respect to y must be equals to partial derivative of n with respect to x. Do we have this? Partial derivative of m with respect to y is 1 minus 2x squared y. Partial derivative of n with respect to x is just 1. Are they equal to each other? Nope. So it's not exact. Exactness doesn't work here for us. So we cannot apply the method of being exact. What else? Can I apply substitution? Maybe. We learned about substitution in different format. Sometimes y equals to vx works for us. Sometimes x equals to uy works for us. Sometimes we see a linear pattern somewhere like ax plus by, that works for us. Some other times, however, these methods of substitution do not work. But if we look at the equation, we might see something similar to this form. Substitution for a form like this. We have dy over dx plus a quantity in x times y equals to a quantity in x times y to a power like n. Dy dx plus pxy equals to qx y to power n. If we see a format like this, then we can apply a substitution method. In this substitution method, your u becomes y to power 1 minus n. When you see an equation like this is a famous equation that they call Bernoulli's equation. So substitution for Bernoulli's equation is u equals to y to the power 1 minus n. Bernoulli. So let us check to see if this guy can be written in this format. Divide everything by x. Divide by x. If you divide by x, you get y prime plus 1 over x times y equals to x, y squared. So far, so good. What I see px, which is 1 over x. What I see qx, which is just x, and y to the n is y to the second. So the substitution that we're going to use is u equals to y to power 1 minus 2. This is your u. 1 over y, or y to power negative 1. What's the next step? Well, remember that here you're using u equals to 1 over y. It means that y is equal to 1 over u, right? What is dy dx? So dy becomes negative 1 over u squared du. Here we have y prime, which is dy over dx. So dy over dx becomes negative 1 over u squared du over dx. So far we have these substitutions to work with. Wherever we see y, we're going to write 1 over u. Wherever we see dy over dx, we're going to substitute that with negative 1 over u squared du over dx. So let us begin. Y prime is now become negative 1 over u squared du over dx plus 1 over x times 1 over u equals to x times 1 over u squared. Very well. So what do we see here? I have negative 1 over u squared, u prime plus 1 over x times u equals to x divided by u squared. Can I simplify this more? Is it possible? What's the format that I see here? If you multiply everything by negative u squared, let's see what happens. You get du divided by dx minus 1 over x times u equals to negative x. Well, this is similar to a linear first order differential equation. So take a look at this. You had a differential equation that was not separable, was not linear, was not exact. So we check to see if we can somehow use substitution. Substitution y equals to ux, ux equals to, for example, vy, or the linear combination didn't work for us. But we can use a substitution u equals to y to 1 minus n because the format of this differential equation is similar to the format of Bernoulli's equation. When we did that, we converted this differential equation into a linear form. Now that you have a linear differential equation, you need to find the integrating factor. Well, what is the integrating factor? The integrating factor is e to the integral negative 1 over x dx, which becomes e to negative ln of absolute value of x, or here you get, if you just move this exponent here, you get 1 over x. If we assume x is positive, you can get rid of your absolute value on 0 to positive infinity. So now you multiply everything by the integrating factor, which becomes 1 over x du dx minus 1 over x squared u equals to negative 1. Well, on the left-hand side, we have the expanded form of the product rule between the integrating factor and u. On the right-hand side, we have negative 1. Now, just take the integral of both sides. The left-hand side becomes 1 over x times u, and the right-hand side, well, here in this case, we get negative x plus the constant of integration. Remember that your original differential equation was written in x and y. Here you have u. We have to get rid of u, but u is 1 over y. So we get 1 over x times 1 over y equals to negative x plus c. Doing algebra, your y can be isolated on one side, and what do we get? We get, for example, 1 divided by, or negative 1 divided by x squared minus cx. You can multiply the numerator, the denominator by negative sign, and you can rename this to k or any other variable that you like, and eventually you get 1 divided by x squared negative x squared plus cx. This is the general solution for this differential equation. So when you see a differential equation, it's important to check to see which method works the best for that differential equation.